So state the conditions for a function to be differentiable at a point. State the conditions for a function to be holomorphic at a point. Um, so, okay. Uh, I mean, the the definition of complex differentiability can be expressed in terms of a limit. Um, but I mean, looking the I feel like I think like they're hinting at the Cauchy-Riemann equations rather, which well the thing is that's not exactly the definition. I mean, looking at B, um, the reason as well I was thinking of Cauchy-Riemann is because in question B we're asked to determine where this certain function is differentiable, and this is really where Cauchy-Riemann equations come into play. Um, but I think because Cauchy-Riemann um is not it's not a well it's you can write down a necessary condition, you can write down a sufficient condition, but you can't write down a single condition like Cauchy-Riemann style, which is both sufficient and necessary. So that's a bit I but then why wouldn't they just say like state the definition? Um okay. I mean, let's do it. Let's do Cauchy-Riemann. I feel like otherwise they just ask us for the definition. So let's be completely precise. So this I'll state as a theorem. Um, so in one direction, there's 2 points I want to make. So if um um okay, bit of setup, right? Let U in C be an open subset, and F be a function from U to C, right? So a complex function. Then one, uh, 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 F is differentiable at Z in U implies that the Cauchy-Riemann conditions are satisfied. But I've yeah, I haven't really set things up properly again. I need to set up some notation. Uh, so write F of X plus IY equal to U xy plus I b xy. So x and y would be the real and imaginary parts of the input, um, and yeah, and then u of xy and v of xy would be the real and imaginary parts of the output. I suppose I should say something like let z equals x plus iy in U. Okay. Then I think I'm all set up now. Then one, f is differentiable at z implies that um, the partial derivatives of u and v satisfy the following conditions. So du by dx at xy should be equal to dv by dy at xy, and sorry, yeah, du by dy at xy should be equal to minus dv by dx xy. So these are known as the Cauchy-Riemann conditions. So that's an implication, right? Two, so maybe yeah. In other let me say, in other words, the Cauchy-Riemann equations are satisfied at point x, y. So that's one implication. And two, I'll say if the Cauchy-Riemann equations are satisfied and u oh sorry, well yeah, well du, all these du dx and du dy, all the partial derivatives are continuous at xy, then uh, then conversely, then f is differentiable at z equals x plus iy, right? So um, yeah, so if f is differentiable, that implies the Cauchy-Riemann equations, and conversely, if the Cauchy-Riemann equations are satisfied and those partial derivatives are continuous at the point, then we can go back and say actually f is differentiable at z. All right. So that's being differentiable. And the definition to be holomorphic at a point, and let me call that a definition, I suppose. That f is a holomorphic at z and c. What that means is that f is differentiable at sort of at w for all w in some in some ball um, BRZ centered around Z, right? Where R is strictly greater than naught, right? So if say if F is holomorphic at Z, then not only it needs to be differentiable at Z, it needs to be differentiable inside a ball centered at Z. Okay, cool. E then, determine where this function is differentiable. And this should be pretty easy. Um, so this function, so f of z is equal to the real part of z plus the imaginary part of z. So if we want to um, use the Cauchy-Riemann equations, we need to find out, you know, what the real imaginary parts functions, the u and v functions are in terms of x and y. So let's see. Well, if we write z as x plus iy, then the real part of z is of course x. The imaginary part of z is y. Okay, and so that's it. And so that's both of those are real, right? So actually this is the real part, and then the imaginary part is 0 for this function, right? So u of xy, the real part is just x plus y, and the imaginary part for this is 0. Okay. Um, so let's write down the Cauchy-Riemann conditions. Well, du dx is equal to dv dy, and du dy equal minus dv dx. Well, those are satisfied in this case, if and only if what? Well, du dx is just 1, and dv dy is going to be 0, and du dy is 1, and minus dv dx is 0. Well, so clearly the Cauchy-Riemann um, equations are not satisfied for any z in the domain of this function, which happens to be C, right? So f is nowhere differentiable. In fact, yeah. Yeah, it's not surprising. These functions that involve real part, imaginary part, they're usually not differentiable, or if they are, they're only differentiable at a few points. There's also a theorem that says that, if uh, sorry, if a function is differentiable and real, then it must be constant, right? And clearly this is real and not constant, so it can't be differentiable. Anyway,